Welcome back. In this lecture, we will discuss different variants of constraint satisfaction problems. So, what are some things that we want to solve for given a constraint satisfaction problem? So first, and perhaps most obvious, determine whether or not a solution exists. We saw in an earlier lecture an example of a constraint satisfaction problem where there was no solution that could exist. The next would be finding a solution. So if there is a solution, can we return it? Finding all of the solutions. What are all assignments of the variables that satisfy the constraints? Counting the number of the solutions. And so this comes up often in cases where we want to maybe reason about something probabilistically. And what's interesting here is counting the number of solutions. Typically, this is going to be sharp P hard, which is one of the highest classes in the polynomial hierarchy. And we could say that if you can count the number of solutions, that is going to be at least as hard, or finding the solutions is going to be at least as hard as counting the number. Because if you can find all solutions, you can count them, obviously. Likewise, finding, if I can find all solutions, it's very easy to find a single solution. Finding the best solution given some quality metrics. So we could also specify some preferences over constraints. You can think of this as an optimization criteria where some solutions are more desirable than others. Determine whether some property holds across all solutions. And this would be called what is a necessary condition, something that is required for any solution to the CSP. And we could think of this as that we have a simple CSP over the real values as the domain, and one of our constraints is x equals 30. Well, we know that x has to equal 30 in any valid solution just by looking at the constraint. But of course, in the general case, this could potentially be much more difficult. So here is an example, CSP for scheduling activity. We have variables A, B, C, D, and E that represent the starting time of various activities. We have the domain of each is simply going to be numbers 1, 2, 3, and 4. So we could say that's 1 o'clock, 2 o'clock, 3 o'clock, 4 o'clock. And any of these activities can have that value. So we have these values, and where we have these domain values, and we have these different variables. And so how many total assignments are there? Well, this is going to end up being, we have 4 values. We can think of 4 values for A, times 4 values for B, times 4 for C, times 4 for D, and so on. And so since there are 5 variables, this is going to be 4 to the 5th total assignments. Now here are some constraints. So for example, B is not equal to 3. This little symbol here is AND. C cannot equal 2, A cannot equal B, B cannot equal C, and so forth. C has to come before D, E must come before C. And so you need to find an assignment that satisfies all of these at the same time. So in this second example, we have a crossword puzzle. Now, what are the variables? Well, let's look at the variables. We're going to say we have variable 1 across. So I'll say V1A. We have variable 1 down, V1D. Let's make that A look a little better. We have 2 down, which is the only 2, so we have variable 2. We have 3 across, which is the only 3, so we'll just call that variable 3. And we have variable 4. So we have 5 variables. So what are their domains? Well, variable 1 and variable 4 would have the same domain because they have the same number of words or letters in the word. So this would be this set here, because that's going to be domain of 1 across, domain of variable 4. All right, so then we've got some 4-letter words. We have book, buys, hold, lane, and year. And our 4-letter word is 1 down. So that makes the domain of 1 down. So the next we have is variable 3, which is a 5-letter word. So we have beast, and ginger is 6, search is 6, symbol and syntax are both 6. So we just have, I'll just rewrite beast here. And that is V3. And then the rest, 1, 2, 3, 4, that's going to be the domain of V2, because 6-letter words. So there are the domains, or the variables and the domains, and how many assignments are there? Well, we can, look at each variable, count the number of assignments, multiply them together. So we have 5 variables. So variable 1 across, that has 1, 2, 3, 4, 5. So there's 5 for 1 across. 1 down also has 5. Variable 2 has 4. Variable 3 has 1. And variable 4 again has 5. So we have 500 assignments. So what are the constraints? Well, we can form the constraints as certain words can go together. So for example, 1 across and 1 down have to share the first letter. So we say that V1A, I'll make that a capital A, V1A can equal big, and V1 down equal buys, or V1A equals big and V1 down equals book. And this would go on and on because they share that position. Likewise, we can look at what the common position here, which is the 4th letter of V1 down and the 1st letter of V3. So as V3's first letter has to be B because that's the only assignment. So we could say that V1 down equals well, actually that's kind of revealing because there is no 4-letter word where the 3rd letter starts with a B. So there's actually no solution to this CSP. So anyway, we can see that, expressing a crossword puzzle as a CSP, there's ways to do that where you can look at the, words that can be associated with the various numbers. The problem can get more complicated when we start to look at, a crossword puzzle like this, and when we allow much more words in the domain. And if we don't restrict the domain like I did in the previous example, and we say, hey, it could just be any of 10,000 words, and we treat the length of the word as a constraint, right away we could see that we have grown the search space significantly, because we're going to have 10,000 times 10,000 times 10,000 for each of the variables. So that concludes this lecture on variants of constraint satisfaction problems. Please stay tuned for more content.